My talk today is on recognizing uranium source rocks in the sedimentary environment. If we look at the historical price of uranium, we see in the 1970s we had a period of time when the price was very high. We were expecting nuclear power to meet all our electrical generation needs in the future. That didn't happen. The price fell and remained low for 30 years. Then, in the mid-2000s, two mines in Canada flooded, and where there was a temporary price spike. The price fell, started to recover, but in 2011, the Fukushima disaster hit, and Japan took all their nuclear power plants offline. Some countries, including Germany, have decided to phase out their nuclear power, and the price fell below production. Production costs in the U.S. are on about the order of $30 per pound. The price was pretty low. Spot price was as low as $18 a pound. More recently, this year, 2020, we've had a price increase of about 40% starting in March. Exploration strategies in the late 1940s and early 50s, direct detection of radiation near the surface led to the discovery of a number of important mining districts. In the late 1960s and early 1970s, we had the roll front model developed by industry geologists working in Wyoming. This model has been extremely successful and is applied to discovering many uranium deposits worldwide in sedimentary rocks. The uranium source for these roll front deposits is thought to be granites and tufaceous sediments. Carbonaceous marine shales are also high in uranium, but to date, no uranium deposits have been linked to a marine shale source. All Cenozoic sandstone deposits that are economic are roll fronts. However, significant sedimentary deposits are not roll fronts. Here we have a diagram, a very simplistic diagram showing a typical roll front. What we have on the upgradient side is oxygen-rich water that has a high concentration of hexavalent uranium. It intrudes into an aquifer that is largely low in oxygen and may have carbonaceous material and or pyrite present. And what happens is that the hexavalent uranium will precipitate out at the roll front as tetravalent uranium minerals, usually coffinite and or uraninite. Now, the uranium minerals aren't very visible, and what was successful about this particular method of exploration, you can drill test holes on the upgradient side. The iron minerals are oxidized. They're very brightly colored. There can be reddish, the hematite, or the yellow limonite. On the other hand, on the downgradient side, the iron minerals are pyrite. So by looking at the drill cuttings, you can locate the roll front deposit where there is high concentrations of uranium. You don't always get uranium. The big question is what factors lead to the introduction of high uranium oxygen-rich water into these aquifers. Here we see a roll front deposit exposed in an open pit mine in Live Oak County, Texas. The oxidized zone is the whitish zone in the center, and surrounding it is the uranium mineralization associated with carbonaceous material and pyrite. This is a typical tabular uranium deposit hosted by sandstones in the Colorado Plateau. What you have is a zone of uranium mineralization associated with carbonaceous material that's completely surrounded by sandstone with pyrite. And essentially, the iron minerals are not a usable guide in looking for these type of deposits. These deposits account for 50 to 60% of the production out of the Colorado Plateau. This is a situation where you have a roll front where the iron minerals have been modified again. You can have introduction of hydrogen sulfide and methane gas by faults. You see this sometimes in Texas. Or you can have generation of methane by biogenic processes. And what happens is the iron minerals will reconvert it back to pyrite. Another example of a roll front deposit that's been modified is when you have leaching or bleaching of the sandstone and you have the iron minerals removed by groundwater that is reducing in nature and slightly acidic. And you can end up with deposits that where the uranium is still in the roll front, but the iron minerals have been removed. And again, the iron minerals are not a guide to this roll front type deposit. There's also miscellaneous sedimentary deposits. There are carbonates. Delta limestone in Grants, New Mexico is one example. And this, in my mind, is part of what I would call the Jurassic-Morrison uranium system. And the source of uranium may be coming out of the Morrison into the Delta limestone. There's also breccia pipes in northern Arizona. These are small deposits that have relatively high grade for sedimentary uranium deposits. Their age dates, most of these, is Triassic in age, and they may be part of what you might be called the Triassic Chinle uranium system. There are mixed types. Unconformity deposits in Canada and Australia are very high grade. There's also hydrothermal deposits in China. Some researchers think that the uranium source for these types of deposits may be shallow meteoric water. The question is, how do we get high concentrations of uranium in meteoric water? If we're going to explore for unconventional deposits, that are deposits that are non-roll front or roll fronts that have been modified, we need to use a systems approach. We need to understand uranium systems. Analogy would be the understanding you have in petroleum systems, where you have a source, migration path, and a trap. We need to identify uranium source rocks for frontier exploration. And we also would need to incorporate paleohydrogeology. Arctic sediments are thought to be a source. I think we'd have to investigate granite sources. Some granites are more leachable than others. If uranium is present in allanite or uranothorite, these minerals are much more subject to leaching and weathering than zircon and monzonite. The USGS has looked at uranium lead systematics and uranium thorium ratios in the Granite Mountains in Wyoming, and it looks like that they may have been an important source for the uranium deposits in Wyoming. Colorado Plateau may have also sourced some of the material from granite uplifts, but not Texas. Texas is strictly a volcanic clastic. In Australia, you have Paleo Valley roll front deposits and a calcrete type deposit, which is totally different from what we're discussing today. Tufaceous source are an important uranium source. If you take volcanic glass, weather it, you form clays which cannot accept uranium into their structure. You can release a lot of silica, and if it's oxidizing situation, you end up with uranium, hexavalent uranium in solution. Volcanic clastics as a source, Wyoming is important, Colorado Plateau, and Texas. Rhyolite glass is high in uranium and easily leached. Petrogenesis is important. Research done by the Bureau of Economic Geology in Texas in 1981 showed that the formation of soil zones will release uranium in volcanic clastics. And research by Bob Zielinski, looking at the White River Group, saw that high thorium-uranium ratios are indicative that uranium has been leached out of the volcanic clastic source rocks. In conclusion, it looks like source rocks in volcanic clastics can be identified. Most likely, they're paleosols with high thorium-uranium ratios. Here we see an outcrop of the White River Group in Badlands National Park, South Dakota. The Brule Formation is seen in the background, the ridge-forming unit. The Shattering Formation is found in the hummocky-looking white area. The only Chamberlain Pass is the interior paleosol in this area, which developed on top of the Yellow Mounds paleosol, which developed on the Cretaceous Pierre Shale. This is a close-up of the Yellow Mounds paleosol in Sioux County, Nebraska. In this particular slide, you can see the yellowish color due to the iron oxides. The carbonaceous material has been deeply weathered, perhaps over millions of years. Here we see the complicated stratigraphy of the lower part of the White River Group in Nebraska and South Dakota. We have a couple potential paleosols that could be source rocks for uranium deposits in the local area. One is the interior paleosol, which is the orangish paleosol that formed on top of the Chamberlain Pass, and in some areas it formed on top of the Yellow Mounds paleosol. In the upper part of the Shattering Formation, the paleosols are rather limited. They're lacustrine limestones, and the water table is fairly shallow. It had limited vadose zone. But in the lower part of the Shattering Formation, you have some oxidizing looking paleosols. Here is an outcrop of the basal Shattering Formation near Red Shirt, South Dakota. There is a great deal of granitic material and metamorphics derived from the Black Hills uplift. This is an outcrop of the basal sand of the Chamberlain Pass Formation in Sioux County, Nebraska. In contrast, the clasts here are largely chert, quartz, and quartzite, very resistant to weathering, very different from the basal shattering sands. What we have here is a combination mud log and electric log through a test hole that was drilled in the central part of Nebraska. And what we see is that we have a gamma characteristic signature where we see when we drill through the weathered paleosol, Yellow Mounds paleosol, and into the Pierre Shale. And typically we have a lower gamma, and you can see where it's labeled weathered paleosol, and then we go into the mottled paleosol, and then we have a sharp gamma spike. Now the colors of these on the left-hand side are not due to the actual color formation. They're assigned by Rockworks to certain lithologies. We'll look at the actual colors of this formation in the next slide. This is a slide showing the shattering clay. It looks kind of grayish on the left-hand side. The Yellow Mounds paleosol is in the next slide, tray over. And then we have a mottled paleosol, which has both weathered and modified Cretaceous shale, Pierre Shale on the right. I'm going to talk about the Crow Butte deposit in Dawes County, Nebraska. Discovery was announced in 1981. It has over 25 million pounds of reserves announced at greater than 0.25%. Production started 10 years later, 1991. It produced about 800,000 pounds per year. The total production is 18 million pounds. It's currently shut in. Operating costs are in the order of about $30 per pound. It is a roll front deposit in the basal White River Group. This slide shows the distribution of basal White River sands in the Nebraska Panhandle. The uranium discovery is in Dawes County. It's marked with a star. That's about a 6-mile zone, about a quarter-mile wide, where uranium has been produced. There's also uranium mineralization clear from the Wyoming border down into the southern part of the Panhandle into Cheyenne County. There's also another deposit that's been drilled that's called the Three Crow deposit. We'll be talking about that a little bit later. And what's notable about this slide, though, we're going to look at some outcrops of the Chamberlain Pass Formation. It's a major tributary coming into that area, and it's labeled in that blue in the uppermost part of Sioux County. What to me is fascinating is that there's no uranium mineralizations on outcrop. And that is, not only is there no uranium on outcrop in that northern blue tributary, but there have been test holes drilled along in that area, that tributary, where also devoid of any sign of gamma kicks or anything else indicating that uranium has passed through the area. Up in this area, the shadowed formation is the upper part, and it's greenish clay. Limited vadose zone. Uranium was probably released, but limited vertical migration. Also, what may have contributed to the lack of uranium is lack of a granitic source. Also another possibility, is there a rhyolitic source in the interior paleosol? And last, lack of reductants in fluvial sediments. What also may have happened in this tributary, uranium may have migrated through, but may not have accumulated. In a recent study looking at radiation damage to quartz grains using cathodoluminescence microscopy in the Three Crow roll front deposit, the researchers found damage in the ore zone, but not up gradient. The lack of radiation damage in up gradient cores suggested never hosted ore. Roll fronts may only move periodically and only form under favorable hydrobiological conditions. They may form and move in response to base level changes. It could be tectonics in the Rocky Mountain area, and may be due to sea level changes in the Gulf Coast. This is that outcrop that we were discussing, which has no uranium mineralization present. We have the Weta paleosol, which is equivalent to the interior paleosol. How is hydromorphic in nature, it has both oxidizing and reducing indications. The white sandstone below is the Chamberlain Pass Formation, and overlying that is a clay plug which formed in an abandoned meander loop. Now that clay plug consists of reddish mudstones and siltstones, perhaps derived from the Spearfish Formation up in the Black Hills. Basal sands of the Chamberlain Pass Formation in that same outcrop. What looks like carbonaceous material is actually manganese oxides. Manganese is mobile under reducing conditions, but it precipitates out in oxidizing conditions. And this is overlying the Pierre Shale below it. At the base of the hammer, we have modified or weathered Pierre Shale. What may have happened is that you may have a situation, if the interior paleosol had rhyolitic material, it may have released uranium into the environment, and it may have gone into that particular outcrop and kept on moving if the conditions weren't right. However, also the interior paleosol may not contain rhyolitic material. It may be actually not part of the White River group, but it might, the Chamberlain Pass Formation, including the interior paleosol, may have been an earlier, prior to volcanic clastic deposition. I think detailed study of the White River group paleosols would be very interesting in regard to locating potential source rocks for uranium deposits in Wyoming, Colorado, and Nebraska. The upper portion of the White River group, the Butte Formation, there are ash beds that range in composition from andesite to rhyolite that are relatively unaltered. We can look at the thorium ratios of those and assume that they are similar in the lower part and the Shadron Formation and the Chamberlain Pass. Mentioned earlier, thorium is not mobile during weathering. Uranium is. We expect to see high thorium-uranium ratios in highly weathered paleosols. We could also perhaps use rare earth elements to characterize what parent material is present in these paleosols. Is the interior paleosol rhyolitic in nature with the parent material, or is it just weathered Yellow Mounds paleosol? What is also fascinating is that there's been a great deal of work done on paleosols in the Morrison Formation and the Chinle group formations in the Colorado Plateau. These have been extensively studied to study climate change and the evolution of dinosaurs, but nobody has really related them to the uranium deposits that occur in the Colorado Plateau. What we have shown is that the Yellow Mounds paleosol is depleted uranium with respect to the Cretaceous Pierre Shale. The uranium was leached out, it migrated downward and was precipitated out at the top of the unweathered Pierre Shale, or it ran off and into surface streams and ran into the Gulf of Mexico. There are two possible uranium sources in the White River group in this particular area. There's the interior paleosol, and there are paleosols in the lower Shadron Formation that may be oxidizing in nature. It could be a source rock. What is interesting is that I believe geochemistry plus paleopedagogy should help us define source rocks when we look for unconventional sedimentary uranium deposits. Thank you. I'd like to acknowledge the Nebraska Public Power District and the Nebraska Department of Environment and Energy, who are our clients in this test hole drilling programs. Also acknowledge Dee Abaca, who has been a great graphic artist and cartography for CSD and UNL for many years. And also like to thank editors of I2M web portal.